For part 2 of this lecture, we're going to talk about the one-sample z-test and the z-interval. So just to keep in mind, we're first going to review point and interval estimation using the standard normal distribution, that is using z-intervals. And then we're going to cover the basic mechanics of hypothesis testing using the standard normal distribution, that is using the one-sample z-test. We're going to use the one-sample z-test or z-interval when we want to make an inference about a population mean mu based on a random sample of data. So recall that we can use the one-sample z-test or z-interval when we know the population standard deviation, sigma. We know that the population is distributed normally, allowing us to estimate sigma using the sample standard deviation s, or the sample size is greater than or equal to about 30, allowing us to estimate sigma using the sample standard deviation s. The key point is one of these conditions really has to hold, because if we use the standard normal distribution model for the sampling distribution, to put another way, as a model for the sampling distribution, and these conditions hold, then we can proceed. But if we have a small sample, and especially if we don't know the population standard deviation, right, we're going to run into problems with our inferences. So let's look at an example using the standard normal distribution as a model for the sampling distribution. So suppose you're a data analyst for a labor relations organization and you want to know what is the average number of hours employed people work per week in the United States. So you collect a simple random sample of 343 employed people in the United States. Now this is a real subset of the American Community Survey, sometimes called ACS, which is conducted by the US government, and it's a random sample of the American population. They ask lots of great questions. So this is what our data set looks like. This is just a sample of respondents. So you can see that the output is truncated, but we have 343 rows or 343 people. And what we're interested in is we want to make some inference. We want to really examine, what is going on in the population, because we have a point estimate for the hours worked. So the single best guess for the mean number of hours worked in the population, it's going to be the sample mean. So we can use statistical software and we can calculate various summary statistics. So we have a mean, a maximum, a median, standard deviation. But for a point estimate for the population mean, the single best guess is going to be that sample mean, x bar, which here we can see is 38.5 hours worked per week. So we'd say, well, that's what we'd expect the population mean mu to be without additional information. Right? So that's our point estimate. But we also want to conduct a confidence interval, or sometimes called a z-interval estimate. So since the sample size is greater than or equal to 30, we're going to conduct a z-test using the sample standard deviation s as an estimate for sigma. So we're going to use a z-interval. This is just what we saw before, where we have x bar plus or minus z alpha divided by 2 times the standard error. We're going to put in s as an estimate for sigma, the population standard deviation, which we don't know. So when we do that, we obtain a value of the standard error of 0.71. That's just the standard deviation that we'd expect to find on the sampling distribution for the sample mean. Then what we can do is we can calculate a confidence interval. Now, just to keep in mind, we're going to set alpha to 0.05. So when we set alpha to 0.05, we're constructing a 95% confidence interval. So we're going to use the values of z alpha divided by 2 of 1.96. So we're going to use negative 1.96 and positive 1.96. What this is going to do is it's going to ensure that we'd expect about 95% of those sample means to be between those values on the standard normal distribution model of the sampling distribution. Right? About 5% of the time, we're going to have sample means outside of that range. Right? So then we can calculate the z-interval. So we have the point estimate, x bar of 38.49, standard error of 0.71, and then we have a value of z alpha divided by 2 of 1.96, which is just based on setting alpha to 0.05. Now we can calculate the z-interval at the 95% confidence level. So that value is 38.49 plus or minus 1.96 times 0.71. And when we do the full calculation, we're 95% confident that the true population mean is between 37.1 hours per week to 39.88 hours per week. So to interpret this interval, we just interpret it as we do before. And again, there are slightly two different ways you can kind of present this result. Right? You can use parentheses, or you can just say it's 38.49 plus or minus 1.39. So we can also word it in two ways. We could say we're 95% confident that the true mean hours worked per week is between 37.1 and 39.88, or we can say the mean hours worked is 38.49 hours per week, plus or minus 1.39 hours. Those are both equivalent. They're both different ways, and you'll encounter both of these interpretations or ways of stating your results when using a z-interval. And with that, we will look at a few examples of working with z-intervals and point estimates based on this standard normal distribution model.